So the first question that I want to ask you is, what exactly is reality?
Oh, great question. What is reality? The standard view right now in science is that space-time is fundamental. That's been the view for at least a century since Einstein's theory of special relativity. And before that, space and time were viewed as fundamental. And objects inside space and time were the fundamental entities that we had to deal with within space-time. And so that's been a wonderful framework for science for a long, long time. It's the physicalist framework that space and time and objects within space and time are fundamental. And that's sort of captured in the modern idea of the standard model of physics, where we have bosons, leptons, and quarks. These are the fundamental elementary particles. And what they are, what particles are irreducible representations of the Poincare group of the symmetries of space-time. So we have space-time as fundamental, and its symmetries, the elementary symmetries, or the elementary particles, are symmetries of space-time. So that's been an incredibly powerful framework. But it's turned out that trying to understand conscious experiences within that framework has been very, very difficult. There have been no successes so far in explaining any specific conscious experience using physicalist frameworks, like something like the taste of chocolate or this smell of garlic. There's no physicalist theory that starts with space and time and objects in space and time and some kind of complicated pattern of activity or structure of space and time that has ever succeeded in explaining any specific conscious experience. And so it's in the light of that remarkable failure, which we can talk about more, that I've been thinking about reality outside of space and time, that maybe we could put consciousness. Well, we have to, not just the word consciousness, but a mathematical model of consciousness. Like we have a model of, we call conscious agents outside of space and time. So that's what I've been working on, is that kind of notion of reality. And remarkably, physicists themselves now are looking for realities beyond space-time. So they've discovered that space-time is not fundamental, that Einstein's theory of gravity together with quantum field theory, it entails that space-time cannot be fundamental. And so it's not just me, but physics that's now saying that space-time, as they put it, space-time is doomed. It's not fundamental. And also some work that I've been doing with my colleagues in evolution by natural selection also agrees that space-time and objects in space-time cannot be fundamental. That turns out to be a theorem of evolution by natural selection. So it's a great opening question, because science has assumed for centuries quite successfully that space and time, or space-time, is the fundamental reality, as well as the objects within it. And now the tools of science and our best theories in science, namely evolution by natural selection and quantum field theory with Einstein's gravity, are telling us very, very clearly that space-time and its objects cannot be fundamental. And so, but science has the tools to go beyond space-time, and so we are probing new realities beyond space-time, which will be fun to discuss.
So you're saying space-time is not fundamental, but science is based off of these fundamentals. So does that change the way we approach science now?
Well, so the methodology of science is still the same. So mathematically precise theories that lead to testable conclusions that you then go test. And in light of those experiments and their results, you perhaps go back and revise your theory. So that beautiful cycle of theory and test, and then redo your theory and test again. That continues. It's just that space-time, that was just a theory. The idea that space-time was fundamental was just one theory. And now our best scientific theories tell us that can't be the case, that space-time falls apart precisely at 10 to the minus 33 centimeters and 10 to the minus 43 seconds. At the Planck scale, space-time ceases to have any operational meaning. There's no operational meaning that can be given to the notion of space and time. And so that structure is actually fairly shallow. The 10 to the minus 33 centimeters is not very deep. If it was 10 to the minus 33 trillion, I might be impressed, but 10 to the minus 33. So space-time is a very shallow data structure, and it was basically the poverty of our technological tools to probe space-time that let us think that it was the fundamental reality for quite a while. But once we get tools that can actually start to probe at 10 to the minus 33 centimeters, we'll be face to face with the limits of space-time. But already our theories are telling us that it's over for space-time. It's not fundamental. But science itself, as a method of inquiry, is left unchanged. I mean, you might think, well, space-time is doomed. Does that doom science? Not at all. The space-time was just one interesting theory that science used for a long, long time, but science is not tied to any particular theory. And as soon as that theory is doomed, that scientists are moving on, and we're actually finding new structures beyond space-time. So this is not just negative news; it's very positive news that there is very interesting stuff beyond space-time that science can actually address with mathematical rigor.
What are the new structures that we've found with the new modalities that we are working with?
So the physicists have found several interesting new structures. The physicists are, for example, Nima Arkani-Hamed and Yaroslav Trinka and their collaborators and so forth. So they found a structure called the amplituhedron, which is a geometric object that could have lots of dimensions. It could have trillions or more dimensions. So it could be very, very complicated. And it's not a structure inside space-time. It's not like something that's wrapped up inside the smallest part of space-time or something like that. Like you think about the extra dimensions in string theory are sort of walled up inside space-time. This is you have to think entirely outside of the space-time box. So these are structures entirely beyond space-time. And the amplituhedron is interesting in part because its volume gives you the scattering amplitudes for processes in space-time. So a particular amplituhedron or facet of it, its volume would correspond, say, to 2 gluon in, 4 gluons out scattering at the Large Hadron Collider. So the volume gives you these probabilities or amplitudes for scattering. And the phase structure of this object, so like the vertices and the edges and all the faces, that whole structure of it, as it turns out, codes for the properties of space-time and quantum theory, locality and unitarity, so that beyond space-time, this amplituhedron can project down to space-time as basically a trivial projection, right? It's space-time is 4 dimensions, maybe 11 in string theory, but the amplituhedron could have trillions of dimensions. So the space-time is trivial, but not only does space-time arise, but quantum theory. So quantum theory is not fundamental either. Space-time and quantum theory arise together from this deeper structure. And then beyond the amplituhedron, because the amplituhedron is just sitting there, it's just this geometric object beyond space-time. And behind the amplituhedron, they found, to their surprise, permutations. Like if you have a deck of cards, like 52 cards, there are 52 factorial ways of shuffling those cards, right? The ace could be first, now you could have the king first or the queen first and so forth, and shuffle the cards. So those are permutations. And they found that permutations with a slight twist, they call them decorated permutations. And if you want, we can go into the technical aspect of it. It's basically permutations with a little twist. Permutations capture most of the interesting information about scattering amplitudes in space-time. And so that's a bit of a surprise. What does shuffling, and shuffling of what? So what's interesting is they found the amplituhedron, the decorated permutations, and a few other structures like the cosmological polytope and associahedron and so forth. But these are like these static structures, like these monoliths beyond space-time, and there's no dynamics. So, and physics usually has wanted to find some kind of dynamical system that will explain things. So they've looked beyond space-time, and there's interesting stuff, but right now it's like these geometric objects that are just sitting there, or the set of permutations just sitting there, and no notion of dynamics. So that's pretty exciting, though. I mean, to find these things beyond space-time that code for the properties of space-time and actually give you the scattering amplitudes. And I should say, now people might say, well, so what? Does it really help us in our practical everyday stuff? And the answer is yes. When you try to compute these scattering amplitudes using space-time methods like quantum field theory and Feynman diagrams, just to do a single scattering event like 2 gluons in, 4 gluons out requires hundreds of pages of algebra just for one event. But with the amplituhedron, it's only like two or three terms. You compute it in two or three terms. You can do it by hand on a piece of paper. So the math becomes incredibly simple. From hundreds of pages to a couple terms on a single page is truly stunning. And moreover, not only does the math get simpler, but they find that there are symmetries that are true of the scattering data, of the scattering processes, that you cannot see in space-time, but you can see once you let go of space-time and go beyond space-time. So there's something called the infinite Yangian symmetry. So what the physicists have found is our best physical theories tell us that space-time cannot be fundamental because it has no operational meaning beyond the Planck scale. They found new structures beyond space-time, like the amplituhedron, and the deepest is the decorated permutations. And when you go there, the math becomes easier and you see new symmetries that you can't see in space-time. So when you have all those things going for you, that's the end of space-time. And the new generation of physicists in high energy physics, of course, this is a special part of physics. Most people are not in that area, but in high energy physics now, the race is on for all these interesting structures beyond space-time and understanding them. They're complicated. So yeah, there's a lot of good work going on beyond space-time.
So we've got to step back a bit. Okay, we've got
Sure.
to go to the fundamentals of understanding what you just said. So
Sure.
you said hadron collider, scattering effects. What does that mean, and then how has it changed? So let's go. What was happening before, and what were the methods before, and what that resulted in, and then what's different now?
Right. So in Geneva, there's this huge object called the Large Hadron Collider. It's a big underground tunnel. It's something like 23 kilometers around or something like that. It's huge. And what they do is they use these fantastically powerful magnets, very like the most powerful magnets perhaps on Earth, or among the most powerful, to accelerate particles, often protons, I think, in the LHC. They take protons and get them near the speed of light, but going in opposite directions. So you have a proton going clockwise and another one going counterclockwise, and then at the last second, or last femtosecond, they direct them at each other, so they smash into each other. And it turns out that protons are not elementary particles. They're big, messy bags of particles like quarks and gluons and so forth. And so when you smash them together, you don't know what's going to really happen. But if you're lucky, you'll get some of these really tiny particles hitting each other. And what happens, what appears to happen is we don't really see all the details, but we see like maybe two gluons go in, and then all of a sudden 4 gluons go spraying out. What happens right there at the collision, we don't know, but we have theories that try to explain it. And if you're doing it in space and time, you start doing these Feynman diagrams with all these virtual particles. You say, well, at the point of collision, there were all these possible virtual particles that were exchanged and so forth. And when you do it that way inside space-time, then the math gets really messy. You get hundreds of pages. So that's sort of what the colliders do. And the scattering then is just, the scattering process is when two particles come in, they somehow interact, and then other particles go spraying out, maybe different particles than the ones that went in. So those are called scattering events. And scattering amplitudes, you can think of amplitudes as just like probabilities. They're complex numbers, so they're not real numbers. Like probabilities are real numbers, but when you take the amplitude squared, you get back to real numbers and you get real probabilities. And it's interesting that in quantum theory, you need to use these amplitudes as opposed to just the raw probabilities to do your computations. So the volume of the amplituhedron then, of this geometric object beyond space-time, it does capture the probabilities, or these amplitudes, for various kinds of scattering events. So that's sort of a basic level introduction to what is scattering and what is the Large Hadron Collider.
So, based on what I'm understanding, correct me if I'm wrong, space-time and quantum mechanics, or quantum is just a small pie of the reality of what actually consciousness is.
Well, so of course now the physicists won't be saying that. The physicists are not saying that there's consciousness beyond space-time. So I'm not putting those words in their mouth at all. That's my own. So the physicists have found the amplituhedron, the cosmological polytope, and the decorated permutations, and they may have no interest at all in consciousness. For all I know. But so they found those structures. What I'm proposing with my collaborators is a dynamics beyond space-time. And for me, the reason I'm looking at consciousness is I'm interested in what's called the hard problem of consciousness. How are our conscious experiences, like the smell of a rose, or the taste of cherries, or the sound of a trumpet, how are these conscious experiences related to what we call the physical world, space and time and particles, neurons, brain activity, and so forth. And the utter failure of my brilliant colleagues and my own attempts to boot up consciousness from, for example, neural dynamics, or from other physical systems, integrated information, or orchestrated collapse of quantum states of microtubules and so forth in neurons. I mean, the utter failure of all of these these efforts by my friends and colleagues who are brilliant to start with something physical, neurons or particles, whatever it might be, and to boot up consciousness. There's not a single win. There's not a single specific conscious experience that has been explained by these. Where you could say this pattern of orchestrated collapse of quantum states of microtubules and neurons must be the smell of an orange. It could not be a headache or whatever. There's just nothing like that anywhere on the table. And so it's that utter failure plus. And by the way, it's utter failure by geniuses. I mean, these are my friends and colleagues. So these are many of them geniuses who are working on this. And so if the problem could be cracked, you would think that they could crack it. And so that failure, together with the insight from physics that space-time is not fundamental, and therefore particles are not fundamental, and also the insight from physics that was awarded the Nobel Prize in Physics this year, that local realism is false. That physical objects, not just, this is a quantum theoretic result, that realism, the idea that objects have definite values of physical properties like position, momentum, and spin when they're not observed, that's just plain false. And that doesn't hold just at small scales. Quantum theory, there's nothing in quantum theory that says quantum mechanics only holds up to this size and it doesn't hold beyond that. No, quantum theory is the general theory inside space-time. So local realism is false. And that also lines up with what I found with the evolution of natural selection. Objects in space-time are not locally real. They don't exist except when they're perceived. They are constructs that we make on the fly as needed. So evolution agrees. Local realism is false because space and time are symbols that we create on the fly. They're like a virtual reality headset. It's a VR headset that we create on the fly as needed. Evolution didn't give us a window on the truth. It gave us a virtual reality headset that lets us interact with reality, even though we're arbitrarily ignorant about its nature. So it's that kind of thing that made me say, okay, space-time is doomed. Local realism is false. We have failed to start with objects in space-time and boot up consciousness. And now we know why, because local realism is false. That's why you can't do it. Neurons, I'll make it very, very clear. Neurons do not exist when they are not perceived.
So what exists? So you're saying that it doesn't exist unless you perceive it. And it's almost like, your virtual reality headset. So what is reality? What is real? Who am I? Who are you? What is the interface that we are interacting with?
Well, so those are great questions. And I should first say that the right answer is I don't know. But as a scientist, I can propose theories, and then we can go test the theories. So I don't know, but here's a theory. And the theory is that conscious awareness and specific conscious experiences within conscious awareness, in the model that I'm working on, are the fundamental reality. And those are just words. We have a mathematical model for those who are interested. There's a paper called Objects of Consciousness. So if you just Google Objects of Consciousness and Donald Hoffman, it's free online, so you can go immediately to it and see the mathematics for yourself if you're so inclined. So it's a mathematically precise model. Just at top level, the mathematics is probability theory and Markovian dynamics. So it's primarily a Markovian dynamical system of conscious agents. So think about it intuitively. is we're proposing that there's this huge social network outside space-time. It's a vast, like the Twitterverse. It's a vast social network. The 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 entities in this network are what we call conscious agents. So they really are conscious. They really do have conscious experiences, and they probabilistically affect the conscious experiences of other agents. Just like if I have an idea and I tweet it, then I'm affecting the ideas of other people in Twitter. And when they retweet or they tweet something new, they're affecting my ideas. And you can see this vast, there's millions of Twitter users and billions of tweets. And so it's a vast social network. And what evolution tells us basically is space and time is just a user interface that we're using. And I'm proposing that it's an interface to this network of conscious agents. So in the Twitterverse, because it's so complicated, you couldn't read all the tweets, you couldn't get to know all the Twitter users personally, but you can look at sort of long-term trends, what's trending in Twitter and so forth. So we can sort of create user interfaces to get a picture of what's happening in the world of the Twitterverse, even though it would be overwhelming to try to see every detail of it. And that's what space and time are. They're basically a user interface, a virtual reality user interface. And just like in virtual reality, if you're playing like a game of Grand Theft Auto in virtual reality and you look over and you see a red Camaro to your right, well, the red Camaro only exists when you look, right? Because you render it then and you see a 3D Camaro. Then as soon as you look somewhere else, maybe now I see a white Porsche over on my left. Well, the Camaro is now gone and now there's a Porsche because I'm creating it as a perception. But if you looked at the supercomputer that's running the game, there is no red Camaro in it. There's no white Porsche in it. There's no cars inside that thing. So the Camaro only exists in your perceptions and only exists for the few milliseconds that you're looking at it and seeing it. And as soon as you look away, the Camaro completely ceases to exist. It's no longer there. You know, in computer science, we garbage collect it. We throw it away. And now we're creating a new data structure, which is the white Porsche. And then as soon as we don't see that, we throw that away. So that's why local realism is false, is because space-time is not reality and objects are not reality. It's a headset. And we're rendering the sun and the moon. We're rendering neurons in the moment that we look at them, and then we're deleting them as soon as we look away. Because space-time and its objects are not the reality. They're just a VR headset. As I said, now I don't know what the ultimate reality is, but I'm proposing that it's this vast social network of conscious agents that then uses space-time as just an interface. And by the way, space-time is not the only possible interface, nor is it the best. In fact, there are countless interfaces that you could imagine. And space-time to me looks like we got one of the cheap models. We got one of the dumbed down, low resolution, only 10 to the minus 33 centimeters, and low dimensional, only 4 dimensions. If I want to even try to imagine something in 5 dimensions, I can't even do it. I feel sort of cheated that I can't even imagine a 5-dimensional object. So space-time is not reality. It's a really low-grade headset, and I'm looking forward to, with the science, maybe we'll be able to upgrade our headsets.
So I have a question though. So like you said that if I'm not looking at it, it ceases to exist. But it's not just me who's perceiving this reality, like the red Camaro. If I'm looking at it and I look away, it's not there in my perception. But someone else is looking at it. And let's say 5 people are looking at the same Camaro. Does it still not exist when they look away?
That's an excellent question, because that's the one that comes to everybody's mind immediately when I talk about this thing. And just imagine that you're playing, again, a virtual reality tennis game, right? So you and your partner put on a headset and bodysuit, and you find yourself immersed on a tennis court, and you have the tennis ball. And I hit the tennis ball to my partner hits the tennis ball back to me. And we can both talk about the tennis ball that we're hitting back and forth. So we're playing a game with what seems like one tennis ball that we're both hitting. But what's really going on there? Well, I have the tennis ball that I see in my headset. And if I turn my headset away, I don't see the tennis ball anymore. And my partner has the tennis ball that they see. And there is a reality behind us, the supercomputer that's coordinating things. So there is a reality that's behind both of us. But if you looked inside, you would see no green tennis balls. There are no yellow tennis balls inside the computer. So there is no tennis ball except the one that I render in my headset and that my partner renders in their headset. And that's the same thing in everyday life. When I look at the moon and you look at the moon, my moon is not the same as your moon. You render your moon, I render my moon. There is some objective reality that we're both interacting with. And we both reduce that reality, which is probably incredibly complicated, into something, a trivial object in space-time that we call the moon. So that's why we can all agree, just like people in Grand Theft Auto playing a virtual reality game of they can all agree that there's a red Camaro on my tail, not because there's a red Camaro in the supercomputer, but because we all are using headsets that are coordinated. So if we have coordinated headsets, then we can talk about a shared reality. Of course, if I'm trying to interact with, say, an amoeba, well, my headset and the virtual reality of the amoeba are going to be so different that it's really hard to communicate. So it's really, we get the feeling of objective reality as an illusion because we have coordinated headsets.
So what's the difference between objective reality and physical reality then?
So a great question. So it's, I think, perfectly fine to talk about a physical reality as long as we recognize that space and time and objects are not the fundamental reality, but they are a kind of reality. They are the reality that I create when I look. So I create space and time, and I create the sun and the moon. I create neurons. So physical reality is a real, in some sense, a real experiential reality that I create on the fly. And then what we're proposing is the deeper reality is this awareness beyond space-time. And this deeper awareness in which space-time is just one mode of awareness, one of countless modes that awareness can take. And so this basic awareness and all the particular conscious experiences that can arise in the awareness is what we're currently proposing as our model of reality. And again, I'm not doctrinaire about it. I'm happy to have somebody propose something even deeper if they can. But all I'll say is that I'm proposing that because we know that space-time can't be fundamental, and because of the poverty of my imagination, all I can think of is, well, maybe consciousness is deeper. So hopefully someone with less, with greater imagination than me will come up with something even deeper.
You've spoken about how our bodies, our eyes, our ears, our nose are limited tools that we use to perceive reality and consciousness. Why do you say that? And a lot of people say, we were evolved in such a way that we can interact with the space around us in such a way and then be able to perceive everything. But you have said that it's a limited tool. Why do you say that?
Well, I say that because it turns out it's a theorem of evolution by natural selection. So, and let me say at the start, I'm going to be talking about the theory of evolution by natural selection because that's the best scientific theory that we have right now in the area of biology. And it's a beautiful theory. I really love it. It's mathematically precise theory. We have evolutionary game theory and evolutionary graph theory and so forth. So it's a powerful theory, but I'm not doctrinaire about that theory either. I fully expect that as science moves on, we'll find deeper theory, but we don't have them yet. So I'm using what we've got, for better or for worse. That's what we have right now. And that's what we do as scientists. We take our current best theories and we push them to their limits to see where they fail and see their surprising implications. So that's what I did with some of my students and colleagues, Brian Marion and Justin Mark, and then were students, and then Chetan Prakash and Manish Singh and Chris Fields and other were colleagues that are working on this with me. Well, we asked a simple technical question of evolution. What is the probability that evolution by natural selection would shape any sensory system, vision, touch, hearing, smell, any sensory system of any organism, humans, apes, pigs, ants, any sensory system of any organism to see any true structures of objective reality? Like perhaps objective reality has what we might call a total order, some structure where things get bigger in a sequence, for example, or a metric or a topology or measurable structure, or some kind of group, a permutation group or something like that. So there are lots and lots of structures that you could imagine might be true of objective reality. So the technical question is, what is the probability, according to the mathematics of evolutionary theory, the probability that an evolutionary process would shape any sensory system of any organism to see some aspect of objective reality? And it turns out we can give a clean answer. The answer is precisely zero. There's no chance, zero chance, that evolution would shape any sensory system to show any true structures of objective reality. And the reason, I think the deepest reason, we found several reasons, but I think the deepest reason is that evolution says that there are these things called fitness payoff functions. And these fitness payoff functions are like the points that you might win in a video game, right? If you're in a video game and you're trying to stay alive and get to the next level, well, you have to collect points as fast as you can without getting killed. If you get enough points in a short enough time, then you can go to the next level of the game. Well, it's sort of like that in evolution. You're collecting fitness payoffs, and if you don't die, which is the big negative fitness payoff, but if you don't die and you collect enough fitness payoffs, then you're more likely to yourself, you won't go to the next level, but your genes will go in your children they'll survive to the next generation. And so these fitness payoffs really rule the game of evolution. And so we ask the question, if the fitness payoffs are going to shape sensory systems to see reality as it is, then presumably they better have some information about that objective reality. Technically, you say they must be homomorphisms of some of the structures in objective reality. They have to preserve those structures. Otherwise, there's nothing in the fitness payoffs that could possibly tune you to objective reality. So we analyzed the technical question. What is the probability that a generically chosen fitness payoff function, just a randomly chosen fitness payoff function, will have information about objective reality? And the answer is probability is precisely zero. When you have, as you take the number of possible states in the world and let it grow to infinity, and the possible number of fitness payoffs values grow to a very, very large number, in the limit, it turns out the probability that any fitness payoff is a homomorphism of any particular structure that you want to pick, it goes to zero as the limit. So there's no information in the fitness payoffs to tune us to fitness. So that's why I say that evolution by natural selection itself is telling us that space-time and even notions like organisms are not fundamental, which is really interesting, right? Evolution is a theory about organisms and DNA. And what evolution is telling us is that the very concepts that we started with to formulate our theory themselves have a limit. They're not; those aren't fundamental concepts. And you might say, well, isn't that really just a self-refutation? You use the theory of evolution to refute evolution.
Yeah.
And that's not the case. What's really going on here is what happens with all the best scientific theories. The best scientific theories are the ones that tell you the precise limits of their own foundational ideas. It's bad science when the scientific theory claims to be a theory of everything. I explain everything and nothing is left out. There is no such thing. So a scientific theory that claims to be that is not a scientific theory. It's a mistake. It's wrong. But a scientific theory that tells you precisely its limits is a beautiful theory, and it may then be useful within the scope of its concepts, and then it can point to the need for a theory beyond it. So it's not just evolution that does this. Like as I mentioned, Einstein's theory of gravity, when you combine it with quantum field theory, that our best science then tells us. So Einstein's theory of gravity assumes that space-time is fundamental, right? It's about the curvatures of space-time. Quantum fields, those fields are defined over space-time. So both theories are taking the notion of space-time as a foundational concept, right? And yet, when you do the math tells you your foundational concept of space-time ceases to have any meaning at 10 to the minus 33 centimeters. So here we're using the mathematics of Einstein's theory of space-time and the mathematics of quantum field theory, which is defined over space-time,
Mm.
to show that space-time itself cannot be fundamental. And that's not just, logical self-contradictions. We should throw the whole thing out. No, that's how science is supposed to work, because we recognize up front that no scientific theory can ever be the theory of everything. So it must necessarily have limits, and a good scientific theory will tell you its limits. So I've had philosophers in particular who have come after this work on evolution to say, look, if you use the theory of evolution to show that space and time and objects cannot be fundamental, then you must be refuting yourself. And they just misunderstand. This is how science must work, because our theories can never be the theory of everything. Your theory will have to either tell you that its own concepts have these certain limits, or the theory itself is just too weak. It's not good enough scientific theory to show you its limits. So that's why I say that space and time and physical objects are not the fundamental reality, because our best scientific theories, namely evolution, natural selection, and physics, both tell us that.
So one, what is the fundamental reality first? And then second, what's the jumping off point from now? So now we know that this is not the fundamentals, space and time. So where do we go from here as a collective?
Well, so what we're doing now is looking for more fundamental realities, right? So the physicists are looking for it as well, and I'm looking for it as well with my theory of conscious agents. What the physicists have done is, you can see the quandary. So we've just learned that space and time is not fundamental. So there's something beyond space and time. Well, what are you going to do? Well, how do you go outside of space and time and start finding stuff outside of space? What you get up in the morning, you have your cup of coffee, you sit at the desk. What in fact are you going to do outside of space time? It's really strange. So what the physicists are doing, they're having great success, because what they're doing is they're saying, okay, can we guess some new theories beyond space, mathematical theories? And these are informed guesses, because we can sort of look at the limits of our current, quantum field theories and so forth, and we can ask. And we also have certain surprises. Like, for example, they found these guys named Park and Taylor back in the 1980s found the surprising formula for scattering amplitudes that was really simple. And it seemed to ignore all these virtual particles in space-time. So you find these little formulas, they go, where did that come from? And then you find a bunch of other formulas. How, if you do it in space-time, it's really complicated, but we happen to discover these little silly tiny formulas that do the job. And they seem to be pointing to some really interesting, deeper reality. So those are the kind of hints that we're leading people on. And there was something called Ed Witten and some of his postdocs discovered these interesting ways of computing scattering amplitudes using what are called the BCFW recursion relations. And again, they seem to be pointing to something really simple, but not inside space-time. And so it was that hint that led Nima Arkani Hamed and his collaborators to say, okay, can we find some deeper object beyond space-time, some integrated object that we can really understand and try to analyze, that captures all these formulas that we found, that shows where they come from. And they did it. So they published that. It's only 8 years old. So 2014, they published this amplituhedron paper. So this is all brand new stuff, right? We've just now, as scientists, started looking beyond our headset. Science, right? For essentially for the last few centuries, science has been only studying our headset. That's what science has been studying. We have this little trivial space-time headset, and we've gotten very, very good at studying that headset. So we did our homework. We've done our ABCs. It's now time to take our first baby steps outside of the headset with the new tools that we learned by studying our headset. And so that's how they've done it. They found these little hints inside space-time, these simple formulas like the Park-Taylor formula and the BCFW recursion relations. And they go, okay, this suggests that there's some, let's go look for some object out there, some structure that will project down to space-time and give us these formulas. And so it took geniuses to do this. Like, these guys are geniuses. And they found the amplituhedron, and they showed that it projects down into space-time and gives you these formulas, these scattering amplitudes, and shows you these new symmetries. And then they found, to their surprise, that the heart of the amplituhedron are these decorated permutations. But what they haven't found, and this is only less than a decade old, right? So this is all new. They don't have any dynamics beyond space-time. So what we've done just in the last few months, I was thinking about this. We have our theory of conscious agents beyond space-time. And I want, of course, to show how space-time emerges from that. So I need to get a mapping from conscious agent, this whole social network of conscious agents, like the Twitterverse I was talking about, how it maps down into space-time as just a headset. How do I get that mapping? So it's a precise mathematics that I want. Now, the physicists gave me a clue just in the last few years, right? They say, okay, well, if you go outside of our space-time headset, you find the deepest structure are these decorated permutations. That's as far as we can go so far. So just a few months ago, I said to myself, okay, can I take our Markovian dynamics? So this is Markov chain dynamics of conscious agents. Can I project that onto decorated permutations? Because that would then, I would start with Markov chain dynamics of consciousness, map it down to decorated permutations, and then the physicists do all the rest of the work. They go from decorated permutations through the amplituhedron into space-time, and they give me scattering amplitudes. In other words, real physics that can come out of this. So I thought, well, that's the obvious path to take. So I said, and surely someone's done this. That's an obvious question. Can you classify Markov dynamics with decorated permutations somehow? So I did a search, a literature search, and there was no general theory. I found one paper that had decorated permutations, one special case of Markov, but this is a general question. How can I take any Markov dynamics and classify the dynamics somehow with decorated permutations? And so my friend and longtime collaborator Chetan Prakash, who's a mathematician, and I solved the problem. It didn't take actually that long. So it's a contribution to mathematics, a new contribution where we can assign decorated permutations to any Markov chain, and we also did it for arbitrary graphs. So we can assign decorated permutations to arbitrary graphs, which are, of course, going to be important for social networks again. So now we have this very, very interesting dynamics, Markovian dynamics, and my attitude about it is physicists perhaps aren't interested in consciousness. They couldn't care, maybe they don't care less about consciousness, but they would be interested in a dynamical system that gives rise to decorated permutations because they're interested in dynamics. So what we've given to the physicists is, you found decorated permutations as your deepest structure, and we've found that there is a dynamics that's even deeper, namely a Markovian dynamics, that projects into decorated permutations. So maybe that's what physics should be studying now, is just the what we call these Markov polytopes. So if you have n interacting agents, then you have what we call Markov polytope M sub n. It's the space of all n by n Markovian kernels. So I should just say, for most people, this may not make any sense. So I'll just say what a Markovian kernel is. So if anybody knows a little bit about linear algebra and matrices, what a matrix is, has rows and columns of numbers.
Yes.
The Markovian kernels that we're interested in are n by n. So they have the same number of rows and same number of columns, and all the numbers in a row are positive, or at least they're non-negative. They could be zero. And they have to sum to 1. So all the numbers in a row have to be non-negative and they have to sum to 1. And if you have a matrix that satisfies that, then it's a Markovian kernel. And all such matrices are Markovian kernels, and all of them describe possible interactions of conscious agents in our theory. Every Markovian kernel is a possible interaction of conscious agents. And so what we found are, then if you look at the space of all n by n Markovian kernels. So it's all these n by n matrices. So say all 3 by 3 matrices that are Markovian. That's the Markov polytope M sub 3. All 4 by 4 Markov kernels is M sub 4. All n by n is M sub n. And so there's this whole collection of Markov polytopes, n-dimensional Markov polytopes for arbitrary n. And each one of them, we claim, contains incredibly detailed dynamical information that's important to physics, but it's beyond space-time, and it projects down into space-time into things that we call spin and momentum and particles. And I'll just say one specific thing, for example, that particles in space-time correspond to in Markovian dynamics, they are projections of what are called communicating classes in the Markovian dynamics. They're not the only projections of these communicating classes, but every particle is a projection of a communicating class in the Markovian dynamics. So we have these specific mappings between Markov dynamics and spacetime.
So what is the implication of all of this? Like what window does this open?
Well, this could give us a completely new window onto physics. For example, we may be able to there are some anisotropies in the quote unquote spins of interactions in the Markovian dynamics of conscious agents that we think may eventually show us why supersymmetry turns out to be false for physical theories. So what we're hoping is that we'll actually show where mass comes from, where the notion of mass actually comes from, and the notion of momentum. What is the deeper dynamics beyond space-time that projects down to the relatively trivial physical dynamics that we talk about in terms of particles and spins and momentum? So it's gonna just, in some sense, it's sort of like this. Imagine a bunch of people that have been stuck in Grand Theft Auto with their headsets on since birth, and but they're really smart, and they figured out after years and years of research, they realized, oh, I'm just in a headset. I thought this was the reality. This is just a Grand Theft Auto headset. And now you tell them for the first time, there's this whole world of computers and software outside of your headset. And you start telling, well, in some sense, the headset world is trivial. Now you're going to go into this whole new world of software and so forth that gave rise to the head. And so that's what's about to happen here. We're opening a Pandora's box. Because right now, all we know is the technology within space-time, quantum theory and Einstein's theory and so forth. What if we actually understood the quote-unquote software beyond our headset that's creating our headset? Think what's possible. If you're, for example, if you're a wizard at Grand Theft Auto, so you know how to drive the car, you can beat anybody else in the game.
It's like God mode, where you are in a position where you are understanding creation.
That's right. So even the wizard is nothing compared to the software engineer who can play with the code and, for example, give the wizard's car a flat tire or take all the gas out of the thing or change the whole geometry of the road and make the wizard crash. So in other words, a wizard in space-time is basically nothing compared to someone who can tool with the software outside of space. So right now we are wizards in space-time. We are now taking the first steps beyond it into the software. And so I'll give you an idea about the kind of technology that I think that this will open up. Right now, we only have technologies for moving through space-time. And so we face Einstein's speed limit. You can only go at the speed of light. So if we want to go to the Andromeda galaxy, which is the nearest galaxy, I mean, it's our neighboring galaxy, it will take 2.4 million years. So you won't make it, your grandkids won't make it, your great-great-great-grandkids won't make it. 2.4 million years is a long time. But that's because we're going through space-time. What if we realize that space-time is not the reality, it's just our headset. And it's a bit of software, and we can retool the software. So we can go to Andromeda around space-time, not through space-time. We can go there directly around space-time. Then we wouldn't need all the rockets and fuels and so forth. We would have completely different technology. So I think that the promise ahead is not that our theory of conscious agents is correct. It's the next baby step. And with that, so when we study these Markov polytopes and really understand, quote unquote, this first level of software outside of space-time, and I think it's just the first level. I think, by the way, there's infinite number of levels. Our own theory tells us that there's an infinite number of levels. So we're going to start at the first level, but even that should probably give us technologies that will appear like magic. So that's the practical. I think there will be technology that comes out of it, but also at a personal level, it changes our vision of who we are as human beings. Most of us think that we are tiny, little 100 kilogram, 50 kilogram, whatever it might be, objects, tiny little objects embedded in a pre-existing space-time. And this new theory that space-time is not fundamental completely turns that around. Space-time is not the fundamental reality, and you are not a little object. What you call your body is just your avatar in a space-time virtual reality. But that's not who you are. You are not an object in space-time. You are something entirely outside of space-time. And you create space-time in everything that you see in space-time. You're the creator of it. So this changes what we mean by our whole self-image profoundly. So I get maybe the technology that I just mentioned, as exciting as it is trivial compared to the change in our comprehension of who we are. We're not little trivial objects inside space-time. We are the authors of space-time. And our what we call our physical bodies, that's not us. That is just our avatars. So this opens up the big question, who am I? I'm not an object in space-time. I'm not a physical body in space-time. That's just incompatible with our best science. So who am I? And this is where now science and spirituality may want to talk. Both may have a piece of the puzzle. Of course, I think there are many insights in the spiritual traditions, and I think that there's also a lot of nonsense. And so there's going to have to be a lot of, back and forth. But I think spiritual traditions have said for thousands of years that space and time are not fundamental, that there's a reality beyond, and that somehow we're part of that reality. Science is now ready to address those kinds of issues with tools, brand new tools that we've never had before. And so I'm pretty excited about the potential.
So, what are your inclinations towards spirituality and, let's say, leaning towards religion? And then also, because at the end of the day, the limitations of our human form are based on the tools that we have, our eyes, our nose. So, wouldn't that affect the way we would be able to decipher the problem of consciousness?
Right. So, great questions. In terms of my attitudes toward, what spiritual traditions, how to use them, and what's most promising, here's my attitude. In science, we've learned, partly from Gödel's incompleteness theorem, that there is no theory of everything. That includes there's no scientific theory of everything. No matter how sophisticated your theory is, we can always find, Gödel says, new statements that are true that cannot be proven within your theory. And if you add those new true statements to your theory, you'll find new ones that are true, new statements that are true but can't be proven. So there is no theory of everything. And so for me, one litmus test of what's interesting is if a theory claims to be a theory of everything and it can't tell you its limits, then it's not terribly interesting. That's going to be true in spiritual traditions as well. Any claim that we have now the infallible final story is, I think, wrong from the get-go. Anything that we say that's dogmatic is the very fact that it's dogmatic. If it is dogmatic, means that it's almost surely false. But an idea put out there in the spirit of here is the kind of idea that seems to have worked in many spiritual traditions, then those are the kinds of things that we need to explore. Where I want the science then to try to take those ideas and to make them precise. Because it's been true that spiritual traditions haven't had a language that's precise enough to really show their own limitations, like we do with space-time. We say 10 to the minus 33 centimeters, it stops. I mean, that's pretty cool when you can say that's where it stops. So we would like the same thing with our spiritual concepts. So I'll be disinclined to pay much attention to dogmatic statements. I'll be more inclined to pay attention to insights that seem more open-ended, where it's more about an exploration kind of thing, both on the scientific side as well as on the spiritual side, because Because we know that dogmatism is just plain false. The very act of being dogmatic means that you are in violation of Gödel's incompleteness theorem. So that's not a good place to start if you're trying to get a deeper understanding. So I don't think we can ever conceptually get a theory of the truth, but there is the question of who am I, and am I really separate from the truth? Maybe I can't know the truth conceptually, but maybe I can know it non-conceptually because I'm not divorced from it. I am that unlimited intelligence. And that's a direction that I'd like to explore as well. And again, we'll never be able to get the final theory of it, but we can get theories that tell us more and more about ourselves, even though they always point to the fact that we can never get the final theory of ourselves. And that's the best we can do. We know that we can't do better than that in terms of theories.
How does death fall into this play? Because when consciousness, and then we say like our physical bodies, but then it's beyond that. This is just a simulation. So where does that end, or is there an end, or what are your theories on it?
So in a physicalist framework in which space-time is fundamental and physical objects are fundamental, and you are your body, right, and your consciousness is somehow created by your brain, then in that framework, death is the end, right? When your brain dissolves, are you hearing any background noise that's disturbing?
No.
This is all good? Okay, good. So in a physicalist framework, when you die, that's it, because when your brain dissolves, then your consciousness is gone as well. But in a virtual reality game, say where you're playing some game where you're shooting people up, and suppose you get your avatar gets shot up and it dies. Well, then you just take the headset off. I mean, that's you're out of the game. You just take the headset off. But that was your avatar. That's not you. That was just your avatar in the game. And since space-time is just the headset, and your physical body and your brain is just the avatar, then that means that the death of that avatar is not the death of your consciousness per se. Now, in some sense, when you're in that virtual reality game, say Grand Theft Auto, and so you have a car crash, you had a quote unquote persona in the game. Maybe you were the wizard, and people knew something about you. You had your own little history in the game. Well, when you take the headset off, you say car crashes, you die in the game, and you just take your headset off. Well, that persona is gone, right? Mm-hmm. And in some sense, that was just the persona you took on in the game, but that's not who you really are. That was just sort of a fun persona for the game. So my story about me, where I was born, my parents, what I did in my life, that's all story of my avatar. With death, you may just walk away from that story and not identify with it anymore, and then move on to another headset. Again, I'm saying I don't know the answer to your question, but and I don't want what I've just said to be a statement that like this is dogmatic truth. Not at all. I'm saying here is a new idea to explore given the current state of our science at this point.
So what is new life? Is that a new consciousness? How is that created?
That's a good question. This comes to what I call portals in our interface, right? So my interface gives me insight into consciousness. So when I'm talking with you, right, we're on opposite sides of the world. I'm in California and you're in the United Arab Emirates. And so we're literally on opposite sides of the world. And I'm only seeing you through pixels on my screen, and you're seeing me through pixels on your screen. And some of the pixels are giving me a real insight into your consciousness, whether you're interested, whether you're confused, whether you like what I'm saying, whatever it might be. So some of the pixels that I call the pixels of your face are giving me a portal into your consciousness. But there are other pixels. I see a wall with little black discs on it and so forth. Well, those pixels are giving me no insight into consciousness whatsoever. But I wouldn't want to say that some of the pixels are conscious and some of the pixels are unconscious. pixels are pixels. So there's no conscious pixels versus unconscious pixels. There's just pixels. But some pixels provide a portal into your consciousness, and other pixels are less useful because the interface has to give up at some point. So my view is that every time a new baby is born, a new portal is open into consciousness. So babies are the technology we have for opening new portals into consciousness. When we understand this notion of portal, when I understand our user interface space-time well enough, then we may be able to get other technologies for opening up new portals into consciousness, besides having babies. And some of those portals may look like artificial intelligence systems, right? The technology may be indistinguishable from silicon circuits and so forth of AI. But if so, it'll be a very different kind of consciousness than the standard physicalist AI kind of typically those approaches of artificial intelligence are hoping that they say if we start with some physical objects, circuits and software, which they're taking as part of fundamental reality, and they have the right kind of complex interactions, like perhaps interactions that mimic neural circuits in the brain, for example, then those physical systems will give rise to consciousness in a way that no one's been able to explain. As I've said, the hard problem of consciousness, no one's been able to give one example that works. So I'm not proposing that. I'm saying that that's wrong, that kind of thing. But what we would have instead is a technology that opens new portals into consciousness in our headset. And so the headset itself, we would figure out new ways to rejig our headset to open up new portals into consciousness.
So right now it's happening, I don't know with what system, but like what we are doing is we're creating new portals with life. And you're saying that soon enough we will be in a position, I might be getting it completely wrong, correct me if I'm wrong, is that we will be able to simulate new portals by ourselves.
Exactly right. That once we've understood at least the first layer of software beyond the headset, maybe we have to go a couple layers. But once we understand that, then we may become sophisticated enough programmers of this reality beyond the headset that we can then reprogram our own headset and open up new portals. And who knows, maybe certain kinds of psychedelic drugs are doing that. Maybe certain psychedelics are, probably most of them are just screwing things up. But maybe one or two psychedelics is partly opening up new portals into a conscious reality beyond space-time. So we'll see.
So what are your thoughts on endogenous DMT? So our body produces that at different stages, like, just before we're about to die. We also have it during times of stress. So how does that play into the fact of opening up portals? Because death is like the seizing of the physical body, and then life itself is opening new portals.
That's a really good question, because in the framework in which this is just a space-time headset and we are consciousness basically playing this game for a while, and so it changes the nature of this isn't the final reality, and in some sense consciousness isn't really fundamentally just about what happens in space-time. It's probably more likely that consciousness tries on this headset for a while, learns what it needs to learn, tosses the headset and moves on to other headsets.
So is that slightly similar to the Hinduism belief of life, and each physical form of life is teaching you a lesson, and then by the end you are complete, and then there's the last of everything, and then all life's physical form of life ceases to exist?
Well, those are the kinds of ideas that I think are going to be very useful for this interaction between science and spirituality to go after. And again, my attitude as a scientist will be always that, just like my attitude toward any scientific theory, which is a careful attention and respectful attention and a critical attention, right? Where you're looking for holes, looking for any reason to try to correct the framework. So I love these kinds of ideas. My own guess is that there's no end to the process, so that there's no. So if a particular Hindu idea is that at some point you arrive, my guess is that maybe we don't arrive. Maybe there's an endless succession of headsets because of Gödel's incompleteness theorem. There's no such thing as the final answer. So you can see where I'd be going. I'd be going, yes, those are interesting ideas, but maybe the part of arriving, maybe that won't be part of it. Maybe you're part that there's this process of trying different realities on. Maybe that will go on forever. So you can see there's going to be this kind of back and forth. And eventually even the Hindu ideas and all the spiritual traditions, Buddhist, mystical Muslim ideas and Jewish ideas, and there's mystical Christianity, like the Benedictine monk kind of thing in Christianity. So these mystical traditions, when you look at all of them, they really have a lot in common. Despite the different trappings of words, when you look at the essence, there's something really interesting in common. And so my goal would be, for example, to have a very ecumenical group from all the spiritual traditions, getting past any dogmas and really talking about the heart of their ideas and looking past differences in terminology and trying to, what is the essence of our idea in Hinduism that's shared with Buddhism, that might be shared with Judaism and Sufism and mystical Christianity. Those, I think, the things that transcend those different spiritual traditions that they have in common are probably going to be the most likely to survive in this next step of trying to, have science and spirituality interact. And then I think there'll be this wonderful feedback, because eventually the spiritual traditions will go, yeah, well, the scientists are latecomers to the party. We've been saying that space-time is not fundamental for thousands of years. And the scientists are now getting on board. But hey, the new kid on the block has something new, these new tools that can now go back and help the older traditions to get more and more precise in what they're saying, and to find out, oh, that was wrong. We need to make this modification, and that was dogmatic, and we need to back off from it. As long as we're open to being wrong, that's the key point. To the moment I say, I know I'm right, is the moment I cut myself off from the learning process. The moment I say, I'm trying to be absolutely precise about what I think I know so far, but of course I'm probably wrong, then you're in the learning process. And so that's what we have to have going forward, is everybody come to the table with what their current ideas are, and then we humbly admit that we could probably be wrong. That's when we start to learn. That's when we really learn, and then we can make progress. But as soon as we say, I know I'm right and I'm not going to change it, then you can't learn. And progress stops.
I want to go back a bit on religion, where we mentioned that there's like the commonality, the thing that transcends everything, and what would make sense. So a lot of Christian, Jewish, Muslim religion, all of it goes back to there's one God. Although in Hinduism, you are God, everyone around you is God. And then there is that similarity where, you are beyond the simulation that you are seeing.
Right.
Which direction would you lean towards with the current information that you have? And I'm not saying that this is the final.
Sure. That's a really great question. My inclination right now, and this is based on the mathematics of our own theory of conscious agents. So it's a theorem of our theory that any collection of conscious agents also satisfies the definition of a conscious agent. So it is a conscious agent. And that means ultimately there is just one conscious agent. So that's a theorem of our current theory. But what our theory does is it says, so I'll tell you the limits there, and then I'll answer your question directly about the ideas about one God versus all of us are gods and so forth.
Yes.
In our theory, suppose you have an infinite number of conscious agents, agent 1, 2, 3, 4, all the way up to infinity. Then any subset of those agents, like agent 1 and 2, together forms a new agent, or agent 1 and 50, or any collection. So that's called the power set of this. It's a set of all possible subsets. Well, so the power set of this countable collection of conscious agents is a new collection of conscious agents. It turns out a guy named Cantor, a mathematician named Cantor, proved that the power set of an infinite set is a bigger infinity. So the countable infinity is what they call Aleph 0, but the power set is Aleph 1. It's a bigger infinity. Well, now you can take its power set. So then you get a bigger infinity, which is Aleph 2, and then Aleph 3. And so all these combinations will be new and more comprehensive conscious agents. But Cantor's hierarchy of infinity is infinitely big, which means we can never get there. So our theory says there is one unbelievably complicated conscious agent because it's the power set of the power set of the power set infinite
Yes.
number of times. But it also says you can never get there. In principle, this theory, no mathematical theory can ever describe that one. So there's where my own theory. So I said a good theory will tell you its limits. There it is. And in fact, our theory will tell you at every step of the game how far you've gotten and how infinitely far you still have to go. So that's why I think that there's right now in our current theory, it leads me to think that there's one fundamental consciousness, and that's what you and I really are. Now in terms of like in Christianity, the standard way that a lot of people understand it is that there's one God, and we're in some sense children of God, right? But
Made in the image of God.
we're made in the image of God, or something like that. But my take is that that's not universally. I mean, that's I think what most Christians would say. But I think the spiritual, the mystical Christians would say something different. I think they would point, for example, to a passage where Jesus, when he was talking about being the Son of God, some of the religious leaders, the Pharisees and Sadducees at his time, took up stones to kill him because they thought he was blaspheming by saying he was the Son of God. And Jesus said to them, why are you trying to kill me? Because in the scriptures, he said, the Bible says, I have said you are gods and all of you are children of the Most High. And so Jesus said, if he calls them gods to whom the word of God came, then why are you trying to kill me? So in other words, when you look, there are hints even in Jesus' own words where Jesus seems to be saying that all of us are not just in the image of God, we are God. And so many religions will say that that there is one God, but when you look at them closer, there's really this hint that, well, you're not really separate from God. Even the idea that you're a child of God. Well, a child of a human is a human. A child of a God is a God.
Yeah.
So my take is that this duality between me and God is wrong. And again, this is just my current idea, and based on the current theory. There's a useful way to talk about lots of different conscious agents. In even our own mathematical model, we talk about small conscious agents because that's all my math can do. The only conscious agents I can really simulate are these finite little ones. So that's what I do. But I know all along that what I'm simulating is just a little bit of the infinite one conscious agent that I know I can never get to. But the fact that I can't get there conceptually or mathematically does not mean that I am not that infinite intelligence. I could be, and you could be, that infinite intelligence. And when we let go of thought, when we actually, like, for example, in meditation, completely let go of thought and just go into pure awareness, we're tapping into that deeper infinite intelligence. We're disidentifying with our little avatar in space-time, and we're re-recognizing the infinite, unlimited intelligence that we are. And this, by the way, if true, this is not just an interesting abstract theory. It's the way that we should do our science. As scientists, if we want good ideas, then we need to step out of our headset for a little bit, meditate, get in touch with that unlimited intelligence, and then go back into our language and conceptual world with new ideas from that unlimited intelligence. So this is not just theory; it's something that we should do in practice, perhaps.
Yeah. We've spoken about how fitness beats truth, and human selection is developed to survive and not to seek truth. What does that mean? Because I'm going back a little bit. I'm going back and forth, but I just want to make sense of certain things.
Absolutely. So this is now just talking about evolution by natural selection and assuming that framework of that theory for the moment, okay?
Yep.
Which is a beautiful theory. So that theory tells us that organisms are shaped by natural selection to have sensory systems that guide adaptive behavior. That is, sensory systems that help you to act in ways that will keep you alive long enough to reproduce. That's what we mean by that guide adaptive behavior. And that's universally agreed to. People who understand evolutionary theory will say, absolutely, that's what evolution does. It shapes sensory systems that guide adaptive behavior. They may do it cheaply. It may be not as adaptive. My sensory system might be not as adaptive as yours, and so maybe I'll go extinct. But that's what it does. It's an extra assumption to say that evolution shapes sensory systems to show you truths about objective reality, right?
Because it has no purpose to do that.
It has no purpose to do that. It's just guiding adaptive behavior, and it's just sort of our. It's interesting. It's just because we are in this VR game, and we've identified with our avatar. We've lost our. It's like if you were in a real good virtual reality game that was so immersive that for a few minutes you actually lost yourself, and you actually felt like, I'm in the game, and this is really me. That's what's going on here. We've got lost in the game, and so now we assume that what we're seeing is the reality because we've been immersed in it. So that's what's going on here. Is we think that space and time and physical objects are the reality because we've got lost in the game, but they're not. And so that's why many my brilliant colleagues who know evolutionary theory have just assumed that evolution would shape us to see the truth because they're assuming we do see the truth. That when I see neurons in brains, that's because there are neurons. Neurons really do exist. But we now know that local realism is false from physics. And we now know from evolutionary game theory that local realism is false from evolutionary theory as well. So neurons do not exist when they're not perceived, and objects don't exist when they're not perceived. They're created on the fly.
So what's the purpose of life?
That's a great question. I don't know, but here's an interesting speculation. I'll tell you what I think it's not first.
Okay.
It's not what most of us spend most of our lives doing. So we spend our lives trying to get stuff like a good house or a fancy car or a reputation, and we know that all that's going to disappear. Everything inside space-time is going to disappear. And so if that's what life was about, if life were about that, then everything that we're doing is life is about something that's completely meaningless. And basically everything that we do, the only meaning that you could give is to say it was the process of doing it itself, but it'll be destroyed. And so, but I think that bit is the process of doing it itself that's the real critical thing. I think that so space and time isn't fundamental. So it's not about getting more stuff or being more important or being more famous or whatever it might be. That's all within the headset, and you're going to take the headset off and you're going to walk away from that. And that's not what it was really about. I think more likely it's about learning. That Gödel tells us, Gödel's incompleteness theorem says there's no limit to the exploration of mathematical structure. No limit, in principle. And if consciousness is all there is, then mathematical structure is only about consciousness and its possible varieties. And that means that there's no limit to the exploration of the possibilities of consciousness, of its possible experiences and structures and so forth. Literally in principle. So maybe what consciousness is up to is the never-ending process of self-exploration that in principle is never-ending because of Gödel's incompleteness theorem. It can never be ended in principle. No one can ever be omniscient. So consciousness is always exploring itself and its possibilities. And what we are here doing is we're in a particular space-time headset, maybe one of the cheaper ones, probably one of the more trivial ones that consciousness puts on. But we're here to learn, and if that's the case, then our attitude is really important. Instead of being upset and anxious and always mad at what's happening, about things that go wrong and so forth, recognize in some sense that there's this unlimited intelligence that's putting itself through this headset to learn stuff, and just enjoy the ride. In some sense, complaining, being upset are the opposite of learning. And usually complaining, it comes about when I say, I know better, and this shouldn't happen. This shouldn't happen. I'm smart enough to know that this kind of thing shouldn't happen. And so I'm going to complain about it. Well, maybe I'm not so smart. Maybe things that I think are going wrong are a much deeper intelligence. And if I just sort of go along for the ride and be open to it, then I will learn what I need to learn. So my guess is something along that is what life is about. It's learning. Of course, if something is going wrong and you can fix it, right? If the lights are out in the house, you can change the light bulb or things like that. I'm not saying, just give up, but
Yeah.
but and that would be part of the learning experience. But the complaining attitude that we typically have, where we're always complaining and moaning, even internally, I think that is a big impediment to just an open attitude of learning. And I think that's what maybe life is about: learning to quit complaining, do what you need to do, but be open to learning, and recognize that any concepts that you have inside, all of my concepts, all of my thoughts, are this trivial intelligence compared to the unlimited intelligence that Gödel's incompleteness theorem tells us is out there. So even all the science, if I know all the science and it's, I know all the theories, even that is trivial compared to this unlimited intelligence. So no matter how far we get in our science, don't complain about things going wrong. Always be open to learning as things go wrong. That's my guess about it.
So, a constant need to learn and curiosity seems to be the precursor for life. Do you feel like that has changed over time? Because we have become very cynical as human beings. Is that an evolutionary need, our need to, adapt? Why is this that human beings are adapting in this manner?
So yeah, we are curious, and you might say that there are other organisms that aren't so curious. So maybe this whole emphasis on curiosity is not that important. Maybe that's just an anthropocentric point of view that I've just put out. But I think that if you look at it a little differently, an amoeba. So there's an amoeba, maybe on my skin or something like that. Well, that's presumably from this framework in which consciousness is fundamental. It's the one consciousness choosing a different kind of headset. It's looking at the world. It's deciding to spend some time as an amoeba. Now, from my point of view as a human being, that doesn't look very interesting. I mean, for me as a human being, other things are interesting. Talking with people, going out to dinner, hiking, skiing. These are science. These are, and amoeba's doing none of that. So from my point of view, the amoeba's life is terribly boring. But I have no idea what it's like from the point of view of an amoeba.
Yeah.
And apparently, from this point of view, consciousness thinks it's worthwhile to explore itself through a projection of itself into an avatar of an amoeba. And so, and another one is an avatar of a cow. So for me, it looks like the cow's just standing out there in the field chewing grass. Pretty boring life, but consciousness wants to spend some time exploring reality through that avatar. And so there are countless avatars, and each avatar is just one little projection of the potential of the whole. And from that little projection, it may be hard to understand why you would look at other projections. I'm so attached to my little projection that I can't imagine a cow projection or an amoeba projection being of great interest. But once again, that's just the limit of my imagination. And we should just always be open to the possibility that we're deeply wrong. That might be the most fundamental thing here is don't take your ideas too seriously. Take them seriously to be precise, but so that you can figure out precisely the limits of your own ideas. So we're precise so we can understand the precise power, but also the precise limits of our ideas. And in some sense, dropping dogmatism is the key point. Dogmatism stops the search. So whenever I know that I know the truth, that's the time where I need to stop and say, wait, okay, I need to back off from that. Where could I be wrong?
Yeah. What are you working on currently? Well, what's keeping you busy? What's keeping things exciting for you?
Well, what's really exciting is that we just submitted this paper that has the map from the Markovian dynamics of conscious agents into a decorated permutation. So that's under review. But now what I want to do is to take the features of the agent dynamics, these Markov polytopes, and ask the question, what specific aspects of the dynamics of conscious agents maps to what we call spin and momentum and energy and so forth in space-time? In other words, we have a little bridge from consciousness through decorated permutations, through the amplitude-hedron into space-time, so that we can now start to enrich the physics. Say what aspects of the dynamics of conscious agents gets mapped into spin and momentum and so forth. So that's what I'm working on right now. I'm looking at something called stopping times in Markov dynamics. So these stopping times are ways they allow me to carve up the bigger dynamics into smaller pieces that are projections of the bigger pieces. So I'm looking at how interfaces of conscious agents might be formed using stopping times, and how we might get, in certain ways, we might get like relativistic time and relativistic mass and momentum coming out of this kind of stopping time projection. So I'm in very early stages of that. But so for me, I feel like a kid in a candy store. We've just taken our first steps out of the headset, and humanity has only been able to step out of the headset for the last 10 or 15 years. This is it. And so we're lucky enough to be the generation that took the first steps out of the headset. So I feel like this kid in a candy store. Like, everything that we've done is very, very important, but it's all been in the headset. We're now going into the software beyond the headset. Oh boy, I'm just rubbing my hands and going, okay, well, but we have to do it rigorously. So I need to nail down, okay, what is momentum? What is spin? And so forth. Get it really, really nailed down, because anything that we do in trying to understand the software outside of space-time, the only place that we can test it right now is inside space-time. So we have to be able to take everything we do and project it back into space-time where we can test our ideas. So even though our space-time theories cannot tell us what goes beyond space-time, they can't tell us that. Nevertheless, they can veto. If we have a theory outside of space-time and project it back in and it contradicts our theories inside space-time, then our theory beyond space-time is probably wrong. So our theories inside space-time, which are like Einstein's theory of gravity, quantum field theory, evolution by natural selection, these are all space-time theories. So they're all ultimately not the truth. They're just theories in our headset. But our deeper theory outside of space-time, it may be conscious agents, but maybe not. But that's what I'm working on, is conscious agents. Has to project into these theories in space-time and get those theories precisely, or a generalization of those theories. But if it doesn't get those theories precisely, then my deeper theory is wrong. So I can actually tell when my deeper theory is wrong. But what we have to do is make these very, very precise projections from what we call the software into space-time. So that's why I'm working on spin and momentum and so forth, because that will give me guardrails on our next steps. When I propose new things about the dynamics of conscious agents, I'll then see, okay, what does it project to in space-time? Am I on the right track or not? So that's what I'm pretty excited about now.
So when is this paper being published? And where can people find that?
So it's under review. The journal is called Entropy. Is the journal. They usually are pretty quick, but reviewers sometimes will give you problems that might take a month or two to resolve. So we'll see. I'm hoping by February or March that the paper will be released. The the title is called "Fusions of Consciousness" is the title of the paper. So, and I can let you know when
Yes.
and if the paper is published. But for those who want to see right now a little bit about the theory, the paper "Objects of Consciousness" that was published a few years ago by me and Chetan Prakash is an introduction to the theory and has some initial connections with physics using geometric algebra.
Who else is working in the same space as you, who you think that you are collaborating with, also in a way working together, not specifically have to be together, because these are the people who are going to completely change the way we understand science, reality, and consciousness?
Well, my direct collaborators are Manish Singh, who's a professor at Rutgers. He's a brilliant cognitive scientist and quite mathematically talented. Chetan Prakash, who's a mathematician and a mathematical physicist, both. He's been my longest collaborators in this. We've been collaborating since 1986. So he and I go way, way back. And any mathematical sophistication in our work is not due to me. It's due to Chetan. He's the mathematician, not me. Robert Prentner, who is teaching at the University of Munich right now. He was a postdoc with me for a couple of years. He's got 2 PhDs in physical chemistry and philosophy of mind. And Chris Fields, he's got a PhD in philosophy and almost a PhD, all but dissertation in physics, experimental physics. And Chris has been a long-time collaborator. We're working on a paper together right now. And then there are a number of others who are working with us. It's still a small group because most of my friends and colleagues in cognitive science still assume that space-time is fundamental and that brains cause consciousness, right? So that's still the overwhelming. So I still have a lot of work to do to persuade, but I'm not too worried about it. I mean, it will happen. I mean, it takes time. Even Einstein. I mean, we're nowhere near the League of Einstein, but Einstein, when he published his paper in 1905, Special Theory of Relativity, that was it for Newton in terms of Newton being the fundamental theory of physics. It was over. But 17 years later, when he was given the Nobel Prize in 1922, the Nobel Committee was very explicit that he was not getting the Nobel Prize for his work on space-time. Not at all. They frankly didn't believe it. So,
Yeah.
the revolution occurs, and the old guard, it takes them a few decades to catch up with it. So this will take a few decades. One reason I'm doing podcasts is to try to get the younger generation. That's my big motivation, is to get the younger generation excited, because it's the younger generation. My generation has to die, but the younger generation will be the one that really explores the software beyond space-time. And I would like to live long enough to see what they discover.
What does the younger generation look like, and what would you tell them when they're just starting off? They're in their infancy of like coming into this field and then developing it.
Well, for those, the development that I think is going to be very helpful in the short term would be for students who have background in physics, mathematics, cognitive neuroscience, philosophy. I have one very talented undergraduate student who is now planning to work on this kind of stuff, and what he's doing is I won't mention his name now because it's early, but he looks extremely bright, and he's doing a triple major in physics, mathematics, and philosophy.
A triple threat.
Yeah, so but he's really, really smart, and he's also going to be working on dark matter experiments at Fermilab and so forth as an undergraduate. So he's got the kind of background and direction, and the guy's really, really smart. So already we're going to be giving him work to do. We're giving him projects to do.
Yeah.
And my guess is that he's so smart that pretty soon I'll be trying to read his papers and trying to keep up with him. So yeah,
Then
that's my hope.
he will take the torch and like lead it further.
Yeah, hopefully, hopefully what we've done will sort of help open the door and get a lot of new students looking at the software beyond space-time. But my fervent goal is that eventually I'm the one that's lagging behind, and I'm trying to read their papers and understand what they've done. That's the goal.
Yeah. Where can people find your current work? Like, are you on social media where can you like, keep up to date with whatever? Do you have a website?
What I typically do is I'm pretty good about tweeting. So I have a Twitter account, and whenever a new podcast comes up or a new paper, or I give a new talk, a professional talk that's available on YouTube or something, I'll give it a tweet link to it. So my Twitter handle is at Donald D. Hoffman, Hoffman, all one word. So all lowercase Donald D. Hoffman. But if you just if you go on Twitter and said just type Donald Hoffman, it'll give you my Twitter handle, and you can find my Twitter.
Perfect. Okay. Thank you so much for taking the time to speak to me.
Thank you so much, Neha. It was really, really a pleasure.